Video, we're going to take a look at a couple examples that involve the formulas dealing with universal gravitation. At this point, you may want to pause the video and make sure that you have these formulas written down, as well as the value for capital G, the universal gravitational constant. Some other key values that are useful that will be made available to you on tests and homeworks and so forth, but still it's good to have them written down somewhere, is the mass of the Earth and the average radius of the Earth. So again, good numbers to have handy. If you look them up on the internet, you're going to get a wide variety of values. These are rounded off. They're the values we'll use in class just to have some consistency in what we're doing. So here's our first question. We're going to determine the gravitational force between a 4.5 kilogram monkey and the Earth. And we'll assume that the monkey, like most monkeys, are near the surface of the Earth, and that gives us a value of R to be using. So we're going to use the formula for the gravitational force, but we're going to specifically use as our R value the radius of the Earth. This is true for, or a good approximation for, anything near the Earth, even as tall as our tallest mountains. This is still a logical approximation for that distance. The radius of the Earth is enormous, on the order of 6 million meters. So being, adding or subtracting a couple of meters here and there just really does not make a difference in this overall calculation, especially since the value of R is going to be squared. So in this case, we would need to know the value of capital G. Again, that's going to be used in every single one of these problems. It is truly a universal constant. It applies to any situation in the universe. We would need to know the mass of the monkey and the mass of the Earth. Those are the two objects that are being attracted to each other. Make sure that they are in kilograms. And then we would need to know the distance between them. And again, what you do here is you always measure between the centers of the two objects. And the monkey is so small that doesn't really matter. But for the Earth, it's really important that you take into account the size of the Earth. Now, how do you make this calculation? You would definitely want to grab a calculator here. But if you don't have a calculator handy, Desmos has a nice one to use. So I'm going to just demonstrate how to do this problem on the Desmos calculator. You can find this at desmos.com/scientific, like it shows up top here. And one of the things that I want you to recognize when you use a calculator like this is that you don't have to touch the buttons that you see on the screen. You can absolutely use the keys on your keyboard to make things a whole lot easier. So first of all, I'm going to put in the value for capital G. So 6.67, again, I'm just using the keys on my keyboard, and then times 10 to the negative 11th. So I could use the times key here, but I can also use Shift 8, which is that little star, and that'll give me the multiplication. Then I need to do times 10 to a power. Now that is not something I can do on my keyboard, so I will have to come over here and click this key right here where it says A to the B power. So this allows you to put in a power of any number that you need. So I'm going to put in negative 11th. Okay, and now I need to jump down from that superscript. So I'm going to use the right arrow on my keyboard, and that puts me down to the regular level. Now I need to multiply that by the mass of the monkey. So I'll do 4.5. Again, I'm just typing on my keyboard. And then I need to multiply by the mass of the Earth, okay, which is about 6 times 10 to the 24th kilograms. All right, so 6 times 10. And again, I'm going to click that A to the B, and it'll bump me up, and I put in my 24. Now this whole thing has to be divided by the value of R squared. A great way to do this is just right away highlight everything in the screen and then either click the divide or click the slash button on your keyboard. And then that's going to turn this into a fraction, just like it showed on my screen or maybe on your paper. It's always a good idea in the denominator to put things in parentheses to make sure that everything stays together. This is divided by the radius of the Earth squared, so 6.4 times 10 to the 6th. Okay, and then I'm going to either use my arrows or use my cursor. I want to move to this spot outside of the parentheses, and then I need to square this. And again, you could use that A to the B key, or they actually have just a squared key on Desmos. Okay, and you can see that all along it's been calculating the values, but here now is my final answer. I'm going to round that off to 43.0, no, I'm sorry, 44.0 newtons. All right, let me get that out of the way. So 44 newtons is my answer. All right, let's take another look at another question. So this time our monkey is going to be an astronaut, okay? He's actually going to have to, of course, be in some sort of a space station, but I just have him pictured out floating in space. And what the problem says is he is 400 kilometers above the surface of the Earth. That is typically what the ISS location is. But there's something a little different about this problem that we need to watch out for. The value of R is from the center of the Earth to the center of the monkey, but that's not the distance I was given. When people talk about distances from the Earth, they don't typically measure them from the center of the Earth. They measure them as altitudes or elevations, and those are measured from the surface. So we're going to have to do a little bit of converting to get this value of kilometers into meters. And then also we're going to need to add in the radius of the Earth so that we get the full value of R. So first of all, converting the kilometers, there are 1,000 meters in 1 kilometer, so we would multiply by 1,000. You certainly can write that all out, but you could also write it in scientific notation, 4 times 10 to the 5th. And then that is this distance here. I need to add the radius of the Earth to get the full distance to the monkey. And so we would add the 6.4 times 10 to the 6th to the 4 times 10 to the 5th. Now again, great time to use a calculator to make sure that you get all the decimals in the right spot. So now we're at 6.8 times 10 to the 6th meters. And we basically do the same thing we did before. It's just changing this value of R. It's still the same masses. It's just the distance between them is now bigger, so we expect the force of gravity to be smaller. And so the monkey, instead of having a weight of 44 newtons, at this location, it would only be 38.9 newtons. All right, what speed is the monkey actually going at? So if he's orbiting, then there's a particular speed that matches with this particular location above the surface of the Earth. And we showed in the last video where that came from, that the orbital speed is dependent on capital G in terms of the units and so forth, but it's the mass of the Earth that matters, not the mass of the monkey. So the mass of the object that is orbiting cancels out within this derivation. It is the capital M, the big mass, that matters. But we would again be dividing by R, which again is from the center of the Earth to the object. So we would be using the 6.8 times 10 to the 6th. Notice that this formula does not involve squaring R, so you need to make sure that you're aware of that. This comes out to be approximately 7,670 meters per second.